welcome to lecture 32. In the last class we have started with the network theorems. So we have seen the how to solve the circuit using superposition theorem and also using Thevenin's theorem. So basically we know that the network theorems will be applicable when I am interested to find out particular or I am interested to find out voltage and current for particular one branch. So in this situation it's of no use to write the mesh equation and nodal equation and solve the circuits. So we can directly go with the network theorems and we can solve the circuit. Okay, so in superposition theorem what we have seen is that suppose I have the network which consists of, let's say, 3 voltage sources and 2 current sources, and I would like to obtain, let's say, particular branch current. So in this case what can be done, you activate one source, maybe voltage source and current source, and you activate one source, deactivate all other sources, means what, nullify the sources. So if I am nullifying the sources, voltage source should be short circuited and current source should be open circuited, and then find out the current. Similarly, next time you activate other source, deactivated all the sources, and correspondingly you find out the other current, right? So in this way you repeat till all the sources has been finished, and then the resultant current will be all the algebraic sum of currents. That is what we have seen. Next, what we seen regarding the Thevenin's theorem. So Thevenin's theorem is also the same thing. That is, in this case what we have to do. So Thevenin's theorem will be giving me the terminal behavior which will be same. So suppose I have this network and okay, and suppose I would like to find out the particular branch current for this. So let me consider that as a load impedance, right? And then what I will do, either I will find out current or you can say the voltage, right? So this behavior and this behavior will remain same. And what is the process? Process is that whatever the, suppose, load you have obtained, say you have found out A and B, then open circuit it, find out the voltage, that is Thevenin's voltage, as well as find out the total impedance, that is ZT, and then express this in terms of the equivalent which is called Thevenin's equivalent, which is Vt, in series with the total impedance ZT, and then connect your load impedance. And now it is very easy for me to compute the current through the ZL or the voltage across ZL also. Okay, so this way we seen, and we have taken one problem also to solve it, and we have solved one problem also, I'm sorry. Then so that we have solved in S domain, because if you solve in S domain it will be very good, or I can say you can solve it quickly. Okay, instead of writing it equations into the differential equations and go with the solutions. So I prefer the Laplace domain, by which you can directly, or it will take it will take very less amount of time to solve it. Okay, also you can use the phasor approach also if the sources will be sinusoidal, right? So let me take one example here. So suppose I have the network like this, which consists of the sinusoidal source, and with this it consists of the resistor with impedance like this. Let's say values are 2J and 2 ohm, and then one more resistor here, and then capacitor, and say one more resistor connected with here one more current source. Okay, so this is my circuit, let's say 3 ohm, then this is minus J ohm, and this is 1 ohm. Okay, and the value of this current source is phi angle with 30 degree, and then voltage source will be 10 with angle 0 degree volts. Okay, and I am interested to find out this current I in 3 ohm resistor. So I observe that okay, this is the sinusoidal source, so it will be better for me to go it into the phasor domain and solve the circuit. Okay, so first thing is that you find out the load means for which I am interested to find out current or voltage. So suppose this is my load now. So now I will open it. So if I do this, my resultant network, let me redraw it. So this way, and there is a current source, 5 with angle 30 degree, and here it was 10 with angle 0 degree volts. Okay, this is 2 ohm, this is 2j ohm, this is minus j ohm, and this is 1 ohm, and this is basically I'm interested to find it. So this is very simple. Now how much current is flowing from here? It is 5 angle 32 degree, and this voltage I would like to obtain it. So what will be Thevenin's voltage? This voltage, where this is 10 angle 0 degree plus the voltage which will be developed here. So current is how much? Current is 5 angle 30 degrees moving in this. Okay, so this way current is moving that way. So this will be positive and this will be negative. Let's say these are my polarities. So what I'll do, I'll take it this 2 plus 2j multiplied with 5 angle 30 degree, and if you solve in polar domain, it comes out 9.32 with angle 45 degree. Now what is my next job? My next job is to compute the Thevenin's impedance, and this can be done by looking into the circuit from which I would like to find out the current or voltage, or from open circuit, and then I will nullify all the sources. So this will be your short circuited, this will be your open circuited. Okay, so what is the Z? Here it is Thevenin's, here it is equivalent impedance is 2 plus 2j, so it is 2 plus 2j ohm. Now once I know Zt and Vt, simply I can obtain I will be equal to Thevenin's voltage divided by Thevenin's impedance, and which is 9.32 angle 45 degree with Zt is 5 plus 2j, and if you solve it comes out to be 3.58 with 23 ampere. Okay, so the equivalent Thevenin's will be like this, ZL, and this will be your Zt, which is 2 plus 2j, and this is your Vt, which is 9.32 with angle 45 degree, and here I would like to obtain what is my voltage or current, and here it was 3 volts. Okay. Okay, so this is all regarding the Thevenin's theorem. Now next theorem we'll see the Norton's theorem. So basically Norton's theorem is the dual of Thevenin's theorem. This also can be used when I am interested to find it out particular voltage or particular branch current or voltage. Okay. So in this, basically what is happening in Norton's theorem, it consists of let me tell you first Thevenin's. In Thevenin's theorem, what it consists of voltage source and in series with the equivalent impedance, whereas it is the duals of the Thevenin. So it means that it consists of the current generator like this, and in parallel with it consists of equivalent impedance, that is this, and then consists of load here. So let me call this is ZL, and this will be my current generator. So let me call Norton current or short circuit current people are using. Here it is the equivalent impedance, so that can be called Norton impedance, or I will call ZT only, it doesn't matter. Okay, and this current is flowing this way, and if I am interested in this current, this can be obtained by the use of, this is my Norton's current, so by the use of current division rule. Okay, so IN is your short circuit current. Okay, and Zn or Z, okay, I'll write particular Norton, so Zn is equivalent to Zt. Okay, so as we know, let us start from the Thevenin's and let us derive this. So as we know, for the Thevenin's, how to obtain the current is, can be written as Vt upon Thevenin's voltage upon Thevenin's impedance plus your load impedance. Now what I'll do, I'll take it Zt as common. So if I'll take it Zt as common, I can write Vt by Zt here 1 plus ZL upon Zt, and this let me write systematically. So your current I will be now Vt over Zt into Zt over ZL plus Zt. Okay, so you look this equation carefully. If you look this equation very carefully, what you observe, this is nothing but the, what is it here, is basically the Thevenin's impedance divided by ZL plus Zt. So this is nothing but the current division, right? So in this, these are the parallel branches where my current is dividing. Okay, so this is basically current division between where to where, between ZL and ZT, and I am interested to find out the current in ZL, so that can be written say like this. Here the current will divide between ZT with ZL, and if I would like to obtain the current ZL, so what it will is VT upon ZL into ZT. Okay, and this VT upon ZT will be your total current. So this total current let me call as short circuit current, or this will be your Norton's current basically, and this current is I where I am interested. Okay, so this way also I can write, and the equivalent Norton's network will be like this, whose magnitude will be Vt by Zt, or I can call it as short circuit current. Then in parallel with it is the equivalent impedance, and then load impedance connected with it, ZL, this is Zt. Okay, and I'm interested to compute this I or this voltage also. Okay, let us take it one example on it. So this example is from FFQO example 7.8. So let me draw the circuit. For the circuit shown in this figure, the figure which I am drawing now, let's say there is a current generator, then in parallel with it is resistor, then capacitor, then resistor, then capacitor, and one more resistor here. These are connected. Okay, and suppose here there is a switch. Okay, and this is open at t is equal to 0. Okay, so this is 0.1 ohm, this is 1 farad, this is 0.1 ohm, this is 1 farad, and this is 0.1 ohm, and I am interested, or the question is to use the Norton's theorem to determine the output voltage V0 of t with zero initial condition. Okay, so to solve this, what can be done now? I have to obtain the V0 of t, that is this voltage, means what will be my load impedance? My load impedance will be this. Okay, because this voltage I have to obtain it. So now I will mark this terminal as A and B. Okay, and I will redraw the circuit here, and as I said, it switch is open, so current will flow in this branch, right? If switch would have been closed, then all current would have been flown in this particular branch. Okay, now let me redraw the circuit. So this is current generator, then there is resistor, then capacitor, and this. Okay, so suppose this current, let's put some number 10 ampere, and let me draw it into, or let me write it into transform domain. So if it is a 10 ampere, what will be its transform domain? It is 10 by S, then this is 0.1, this is 1 farad, so it will be 1 by S. Okay, and this is 0.1 ohm. Okay. So first I will obtain the short circuit current. So for that, this terminal, let me short circuit. So if I will do the short circuit of it, what I would like to obtain, I would like to obtain total ISC. Okay, so this is my short circuit current. So how to obtain it? To get it, this I know this current, that is 10 by S, and this current can be obtained by taking the equivalence of this, which I observe that 0.1 and 1 by S are in parallel. Okay, and then I can use the current impedance, current division rule, that is to compute this current is, say this I will call as Z1 impedance. So ISC can be obtained as 0.1 divided by this 0.1 plus 0.1 plus this impedance into total current. Okay, so to find out this short circuit current, how can we do it? That is your total current, which is 10 by S into this Z1. So let me first draw, calculate Z1. Z1 is 0.1 is parallel with 1 by S. In short, R is parallel with CS. So R over CS upon what it will be, R plus 1 CS. So what is this? This will be R divided by 1 plus R CS. Okay. So R is 0.1, C is 1. Okay. So it will be, and this will be Z1. So let me write Z1 upon Z1 plus 0.1. So which is 10 by S into 0.1 over 0.1 S plus 1 divided by again Z1. So which is 0.1 divided by 0.1 S plus 1 plus 0.1, and this is 10. If you solve it, this is 10 by S 0.1 over 0.1 plus 0.01 S plus 0.1, and again you solve. So this can I write as 10 by S 1 over 0.1 S plus 2. So this is my short circuit current or Norton's current. And next, what I would like to obtain, I would like to obtain the total impedance. So for that, this has to be nullified source. So this, which is independent source, has to be nullified. If there will be dependent source, you have to take it into consideration, right? But if it is an independent source, then you nullify it. So this is current source. So take it this open terminal and you look it from this. So what is the the total impedance here? ZT will be 0.1 in parallel with 1 by S plus 0.1. Okay, so here ZT will be 0.1 plus 0.1 upon 0.1 S plus 1. So this, if you write it, it is 0.1 S plus 2, and this is 0.1 S plus 10. Now what is the equivalent of Norton's? That I have to draw the equivalent circuit. So which will be the current generator with value 10, with value ISC whatever we obtained, okay, in parallel with ZT or Zn, and then there is a load impedance. So what is that load impedance? It is your Z2, and what is the load? Again it is R with C in parallel. So what is the load? Load is again R parallel with C. So this is same 0.1 over 0.1 S plus 1. So here ZL is 0.1 over 0.1 S plus 1, and this is what voltage I have to obtain it, or V0 of t. Okay, and this is ZT, and this is my short circuit current or Norton's current, and which short circuit current is this. Okay, so from that I can directly obtain the V0 of t, and let me write in Laplace domain. So what is the voltage across it? It will be this current into this voltage, this current into this total impedance. So again I observe that these are in parallel, so it will be ISC into ZT in parallel with ZL. So ISC is this, which we obtained, into ZT and ZL are same. So means 0.1 S upon 0.1 S plus ZT is not same. ZT is 0.1 S plus 2 upon 0.1 S plus 10. Okay, so ZT is 0.1 S plus 2 upon 0.1 S plus 10 into ZL is 0.1 over 0.1 S plus over 0.1 S plus 1 over the addition of it. So 0.1 S plus 2 over 0.1 S plus 10 plus 0.1 over 0.1 S plus 1. Do simplification. So I got it after simplified form by putting ISC also. Okay, what was ISC? ISC is this. Let me write here on ISC also, 10 over S into 1 over 0.1 S plus 2. So if you simplify it, I got it S 1 by 100 S square plus 1 by 100, 37S plus 3. It's 31, not 37. It is 31 by 100 into S plus 3. and now you can use the partial fraction. So there are the two roots, so there will be the partial fraction a upon s plus b upon this root plus c upon this root, and if you find out the inverse, then you find out the inverse, that is v0 after using the inverse Laplace transform. So my solution is 0.33 plus 0.75 e raised to minus 15.5 t into sine of, it will be 0.7 t plus 117 degree into u of t. So this will be your damped sinusoidal. Okay. So this way you can solve for the Norton's theorem, or you can solve the circuit using Norton's theorem. Okay. Now next theorem is the reciprocity theorem. Now we will quickly see the theorems, as already we know how to solve it. Okay. So reciprocity theorem, basically it is in a linear bilateral and passive network. So it is the ratio of response to excitation is constant, even though the input and output terminals are exchanged. What does it mean? So what I have defined, let me repeat it. So in a linear bilateral and passive network, the ratio of response to excitation is constant, even though the input and output terminals are exchanged. For example, let me see, if I have a network N, okay, to this I have applied this voltage like this, and I'll measure the current here. Okay, so this is my voltage and I measure the current here. Now let me exchange the input and output terminals. So I will apply source at this side, okay, and I will measure the current here. Okay, then I'll take the ratio of response to excitation, so I upon V for this, and this also response is I and the excitation is V, so both will be equal. So if this is the case in any network, then that network is reciprocity, means that network satisfies the reciprocity property, that is ratio will be constant. Okay, for example, let me take one example. So suppose this is the source connected with 4 ohm resistor, then in parallel way 2 resistors are connected, that is 12 ohm and 12 ohm. Okay, so now prove this reciprocity theorem. So voltage source is some number, that is 10 volt. Okay, so what is to be done? I have to obtain, this voltage has been given and I have to obtain the response. So suppose this is my I. Okay, first time, so what I'll do, I'll find out the ratio, that is I divided by V, and then next time what I'll do, I'll change the terminals. So this voltage source will be here and this will be 4 ohm as a load, and I can obtain the current here. And let me check it out, what is this ratio. So to compute this I should know this current, right? And this current how can I obtain? If I'll take it this equivalent, that is 12 ohm is in parallel with this 12 ohm. Okay, so I'll get it single resistor, and then this 10 divided by 4 plus this total equivalent resistance will be giving me this total current, and then I will use the current division rule to find out this current. Okay, so let me find out if 12 and 12 are in parallel, means they are in parallel form. So what is its equivalent? Equivalent will be 6 ohm. Okay, so this is 4 ohm and this is 6 ohm. Okay, and now I'll find out this total current. So total current will be voltage divided by the, now resistance is 4 plus 6, so it will be 10. So now total current is 1 ampere here. Okay, here 1 ampere, now this is 1 ampere. So but what I am observing here, that the resistance are same, so the current will divide in equal amount. So this will be 0.5 ampere and this will be 0.5 ampere. No need to calculate again, because that also you can obtain. I is equal to 0.5 divided by I is equal to 12 into 1 divided by 12 plus 12, so you will get it definitely 0.5 ampere only. Okay, so here now I got 0.5 and V was 10 volts. So what is the ratio of response which I have taken to the excitation? It is 0.5 upon 2, so it is 1 by 20. Okay, now let me change the orientation. So now what I'll do, I'll put it the source here with the 12 ohm in series, and then 4 ohm I'll take it as load. So this will be my 4 ohm, then this will be 12 ohm, and this will be 12 ohm in series with voltage source. Okay, so this is my voltage source with value 10 volt. Now I would like to obtain this current. Once I know this current, I'll be able to know what is this current. So I'm interested in this I. So this current can be obtained by taking the parallel form of 4 with 12. So 4 is parallel with 12, so it is coming out 48 divided by 16, so which is 3 ohm. Okay, so your equivalent will be, this is 3 ohm and this is 12 ohm, and then your source was V, which was 10 volt. Okay, so how much is total current here? Total current will be 10 divided by 15, so this much is total current. And now 10 divided by 15, this ampere is divides here and here, so your I will be 10 by 15 into this division branch, which will be 12 divided by 16. Okay, so if you solve it this way, then 3 and then 4 and then 1 by 2, so it is 1 by 2 ampere. So this I is 0.5 ampere, and then I will take the ratio. So I upon this input is V excitation, so how much it is? 0.5 upon 10, which is again 1 by 20. So observe that even though I am changing the orientations of the source and response, I am getting the same value, same ratio. That's why this network satisfies the reciprocity theorem. Okay, so with this, reciprocity theorem has been verified. So this is applicable only for the bilateral linear network and also passive. Okay, if network contains the control sources, then this network will be active network, and so reciprocity theorem fail there. Okay, then next theorem is the substitution theorem. Substitution theorem. So substitution theorem statement is that in a linear network, any branch can be replaced by different branch, provided that the remaining network voltage and current are undisturbed. Okay, and the new branch voltage and current must be same as the previous one. I am repeating again, in a linear network, any branch can be replaced by different branch, provided the remaining network or the circuit voltage and currents will be not changing, they are undisturbed, and the new branch voltage and current must be same as the previous one. For example, if I have a network and to this I applied excitation like this, okay, E, and this is my current through resistor R. Okay, so what is the voltage drop here? It will be I into R. Okay, so this E is the voltage applied to network, I is the current flowing in load, so voltage drop across R is IR, and now this resistor branch can be replaced by a different branch, provided that network current and voltage must be same. Okay, so this branch can be replaced by either voltage source or current source. Now if I would like to replace this branch by voltage source or current source, so the value of voltage source will be the voltage drop across that particular resistor, and current source will be the value of current generator will be again the current which was flowing through it. Okay, so for example, this let me draw once more. So this is the network, this was the excitation I applied, and now if I would like to replace this branch resistor branch with voltage generator. Okay, so this value of this voltage generator has to be equal to the drop across R, which was I into R, so that remaining network voltage and currents will not disturb. Okay, so that I can replace by voltage source, or I can also replaced by current source also. Okay, and with value with value I. Okay, so conclusion is that any passive element in the network can be replaced by an ideal voltage source or ideal current source, provided the voltage and current in the element and source must be same. Okay. To illustrate this, let me take one example. So this is my voltage source with this resistor here, one resistor here, one resistor here, then there are two parallel resistances, and then one resistor here and one resistor here. So this is E, say R1, R2. For this, some number is given: 2 ohm, 1 ohm, 3 ohm, 5 ohm, 5 ohm. Okay, and it is given that voltage across 2 ohm resistor is 20 volt. Okay, so the question is, what is the voltage source between terminal A and B? Okay, if the A and B terminal replaced by voltage source, so how much will be the value of voltage source and how much is the value of current source if it will be replaced by current source, for example. Okay, so now to do that, what I have to do, I have to obtain how much is the current here, so that I will know what is the drop across it, and once I know the drop, I can simply replace this passive element by its voltage generator, or if I know the current, I can simply replace by its current generator in that particular branch or in this branch. Okay, so for that, what I should know this total current, and this total current I can obtain by knowing this current. Okay, and it is given that the voltage across 2 ohm is 20 and this resistor is 2. So what will, let me directly write without calculating much. So what will be this current? It will be 20 by 2, so which will be 10 ampere here. Okay, and this 10 ampere divide here and here. But again, what I observe here that, okay, suppose if I have the network like this, and this is my I1 current, so it is dividing here and here, but here what I observe at this point, this I1, that is outgoing, and this incoming current will remain same. So if at this point 10 ampere, what about here? Here also 10 ampere. Now this 10 ampere will divide in this particular branches, so I would like to obtain this I. So this current I can be obtained as total current is 10 into this opposite resistance, that is 5 divided by 10, so which will be 5 ampere current here. Okay, so how much should be the value of voltage which should be replaced? So drop across this R will be 5 with resistance is 5, current with 5, so it will be 25 volt is the drop across R, and then this can be replaced by 25 volt. Okay, so I'll quickly draw the circuit. This resistor, and then I would like to replace this by voltage source. So what should be this value? This value should be 25 volt, so that remaining thing will not change. R1, R2, this was 2, 1 ohm, 3 ohm, 5 ohm, etc. Okay, and now if suppose I am interested to replace it by the current generator, so what can be done? It will be replaced by current generator here. Okay, and what should be the value? The value should be 5 ampere. Okay, so this way you can verify this theorem. Okay, the next theorem is, okay, which theorem we have seen now? This was substitution theorem. Now next is Millman's theorem. So Millman's Millman's theorem. So this theorem basically is used when I am finding it out in network that it consists of, let's say, the Thevenin's equivalent network in parallel form. The Thevenin's equivalent network in parallel form means, suppose I have voltage source in series with resistance, voltage source in series with resistance or its impedance if they are in parallel form. So Millman theorem will be used to find out its equivalent. Okay, and that it is, I'll tell you how. So according to Millman's theorem, basically n Thevenin's equivalent in parallel form can be replaced by, in short, single Thevenin's equivalent. So suppose I have the n Thevenin's equivalents here. So one voltage source here, then this in parallel form, one more Thevenin's equivalent with this terminal, one more Thevenin's equivalent with like this. Say I have this way. Okay, so I observe that there are the n Thevenin's equivalent in parallel form. So let me number it. This is R1 Thevenin's, R2, R3 Thevenin's equivalent impedance. This is Rn, and say this is my V1, V2, V3, like Vn. Okay, so this according to Millman says that this should be replaced by its single Thevenin's equivalent, which will be like this one, and then voltage source. Okay, and this will be your Rm, and say this will be your Vm. Okay, and the value of Vm can be computed as V1 G1. Remember that you just check it out the polarities. Okay, so here positive negative, if you are taken this way, then this observe that -1 plus, so it will be next minus V2 G2, here positive negative, so it is V3 G3. Likewise this is negative positive, so it will be minus Vn Gn, and over the sum of admittances G1 G2 or conductances G3 plus Gn. This is nothing but your Vm, and then you can obtain what is your Rm. So your Rm will be 1 over G1 plus G2 G3 like plus Gn. Okay, this is basically Millman's theorem. So what it says, if I have n Thevenin's equivalent in parallel form, that can be simply replaced by single Thevenin's equivalent with Vm and Rm, and Vm can be obtained using V1 G1 minus V2 G2 like this, divided by G1 plus G2 plus Gn, and Rm can be evaluated as 1 over G1 plus G2 plus Gn. Okay, to illustrate that, let me take it one quick example. So suppose I have this resistance with this voltage source in series with it, next this in series with it, one more, then one more voltage source, and say now the situation is like this. Say this is 2 ohm with 4 volt. Okay, this is 2 ohm, this is minus plus 12 volt, this is 1 ohm, this is plus minus 2 volt, and this is 3 ohm. Okay, and I am interested to find out this current I. Okay, so what I observe that it is voltage source in series with resistances, and this can be simply, according to Millman's theorem, it is simply replaced by single equivalent, which is Rm in series with Vm. Okay, and what I have to obtain? I have to obtain the current through 3 ohm. Okay, so I should know what is Vm and Im. So no need to write the equations and all. You can simply use the direct equation, which is Vm, which is equal to V1 into G1. So 4 upon 2 minus 12 upon 2. See, you check the polarities also. Okay, plus 2 upon 1 divided by G1. So 1 by 2 G2 is 1 by 2 plus G3 is 1 by 1, so which is 2 minus 6 plus 2, which is minus 1 volt. Okay, 0.5, 0.5, 1 plus 1, it is 2, so it is minus 1 volt. So this Vm will be minus 1 volt. Okay, and then next I have to obtain Rm, so which will be 1 over G1, so it is 0.5, 1 over G2, 0.5 plus 1, so which is 1 by 2, which comes out to be 0.5 ohm. So this will be 0.5 ohm. Now I would like to obtain this I, so I will be simply equal to minus 1 volt divided by 0.5 plus 3, which will be 3.5 ohm, which is minus 2.7 amps. And with this polarity I'll indicate that this is not the correct direction, but this is the correct direction. That way you can check it out. Okay, then next theorem is Elegance theorem. And it says that in any network the algebraic sum of power at any instant is equal to 0. Means what? Whatever the power absorbed in the network will be equal to power delivered. Okay, so basically this is the power audit. Okay, so and the examples on it already we have seen during the nodal and mesh analysis. We have seen how to calculate or how to do the power analysis, how to do the power audit. Okay, so no need to take the example. So the Elegance theorem simply says that it should satisfy the power audit. That's it. Okay, the next, maximum power point transfer. This also you know it is already you studied. So maximum power transfer theorem. So this is the theorem by which you can find out what is the condition when you will get the maximum power, or when you will be able to transfer the maximum power from the source. So suppose this is my Thevenin's voltage Vt in series with Rt or Zt, and it is in load RL. So this is Rt, this is Vt, and this is RL, and this current I. So how much power will be absorbed by RL? It will be I square into RL, and what is I will be Vt upon RT plus RL whole square into RL, and this is my power. Okay, and I would like to find out how much is the maximum can be obtained. Okay, so to check it out or to obtain the maximum power, what I will do, I will differentiate this to find out the maximum. So differentiate this with respect to DRL, so it will be Vt square into second square, so RT plus RL square into derivative of first one minus first into derivative of second, okay, divided by second function square, so RT plus RL square, and this has to be equal to 0. If this is the case, then what it will be, this RT plus RL its square will be equal to 2RL RL plus RT. Okay, and then what I will do, this will cancel with this, so your RT will be equal to RL. So your maximum power will be transferred when your Thevenin's resistance will be equal to load resistance. Okay, and in terms of the impedance, if I would like to say what will be the condition, okay, let me calculate first power. So power will be Vt, and Rt and RL has to be equal, so it will be 2 times RL, so it will be V square Rt divided by 4 RL square into RL, so which is V square Thevenin's voltage square over 4 RL. This is for resistive network. And if it is impedance, what will be, this will be Zt and this will be ZL. So maximum power will transfer when ZL will be equal to Zt, but I observe that these are the complex conjugates, and in order to get the the real value, what should be, your ZL should be the complex conjugate of the Zt. Okay, so if it is ZL is array R plus J XS, so what will be Zt, or Zt will be R plus JXS, what will be ZL, it should be R minus JXL, then only maximum power can be transferred. Okay, So these are the different, the theorems which can be used for the design of circuit during circuit analysis, and this also can be used to solve the circuits with ease. Okay. So with this we stop here. Next class we'll start with the network functions. Okay. So thank you very much.